Today we will talk about work and energy. What is work? When you lift anything or push something, you get tired after a while. Why is it so? It's because you're spending some energy, some effort you're doing some work. Okay. So we understand work that some effort is to be done to achieve something like lifting a bucket of water or pushing a car, things like that. But can we define it? Yes, okay, let's define it. Work is defined as you have a force which you applied to somebody and it makes a displacement R. Sorry, this is a dot product. Since this is a dot product, this is a scalar, and this will be R cos theta. And mind it, work is a scalar quantity, not a vector quantity. So what it basically means is that when you apply force, you cannot directly multiply by the displacement because there's a cos theta involved. So we can define work as displacement times the force in the direction of displacement. Basically, this portion then becomes our portion of force which is applied in the direction of displacement. Okay. Now, it is not necessary that your force should remain constant or direction of R should remain constant. No, not at all. So what we do is we can always define a small dw which is equal to F time dr. Okay. And if we want to find the complete work done over a cycle, we simply integrate both of them, right? So this will give us total work from stage 1 to stage 2. The F could be varying, dr could, direction of displacement could be varying wherever. Okay. There's another term called power. Now power is defined as rate of doing work, or it is work performed over a period of time. This is power. Now we talk about potential energy. What is potential energy? This is an energy which a body may possess because of its position with respect to a datum. There's a ground. There is some object lying here. And if you lift it, bring it to this position, what you have done, you have lifted, let us say, by a height of h. You have spent some effort in lifting from here to here. Where does that effort go? This effort gets stored into the potential energy of this object, which is purely because of its position with respect to a datum. In this case, it is ground. Now, it is not only a position with respect to height, it could be In case of springs, you have a spring. Let us say this is a spring lying in an unstretched position, and you apply force to stretch it. It stretches. Let us say you stretch it by a distance of delta x. Now what happens is, the force that you applied, you have done some work to stretch it. This work gets stored in spring. And this energy which is stored in the spring is called potential energy. Okay. Unlike potential energy, there is another term called kinetic energy. Which is purely because of motion of a body. So kinetic energy is equal to mv square by 2, where m is the mass of the body, v is the velocity of the body, so because of velocity v, a body of mass m will acquire some energy, which is called kinetic energy. As we have briefly explained earlier the concept of a spring, let us see some more properties of a spring. Spring is a metallic wire coiled together, and it is so elastic that if you pull it, it will extend, and if you push it, it gets compressed as well. Okay. So let us see, this was our original spring. If you apply force in this direction, it extends, stretches, we call it, it's in a stretch position. The reverse could be that your spring was here and you applied force to it in this direction. The spring gets compressed. Now, you apply force in either case, whether you want to pull it or push it. The force applied on a spring is equal to minus kx. X is the distance to which distance of stretching or compressing. In stretching, you elongate a spring. In compression, you shorten the spring. A is called the spring constant. This term means the force applied to stretch a spring or a compress a spring is directly proportional to the distance it is stretched or compressed. Why this negative sign? Because when you stretch it in this direction, the spring applies a negative force, equal and opposite force in the other direction. That is why it is called, there is a negative sign here. Now let's find out how much is the work done if you compress a spring by a distance x. Can we find out the work done? Okay. We cannot find work done simply by multiplying f into x. Why? Because f is varying with respect to x. So what do we do? What we do is we define small work done, which is equal to, okay, and what is this f? This is, so Now we can integrate both the sides, and what we get is W is equal to K So W from initial stage to final stage can be given by x going from 0 to x from x. So work done in stretching or compressing a spring is minus kx square by 2, where x is this displacement. Displacement in case of spring, it will be either how much you have elongated it or how much you have compressed it.